Okay, we have seen in the last video how a magnetic coil inside, or how a current coil inside magnetic field will introduce a torque, and we have seen that the torque would equal the number of turns of the coil multiplied by the current in the coil multiplied by the area of the coil multiplied by the magnetic field applied to the coil multiplied by sine the angle between the normal to the coil and the direction of the magnetic. And we have obtained this simple rule. It is N multiplied by I multiplied by A multiplied by B multiplied by sin theta. Effectively, the part which is NIA is the parameters of the loop itself. And these parameters combined together, we will call it vector magnetic dipole moment, and we will use a symbol mu for this value. So mu, which is the vector magnetic dipole moment of a loop, is the number of turns of this loop multiplied by the current of this loop multiplied by the area of this loop. The remaining part, what is the direction of this vector magnetic dipole moment? To obtain the direction of this vector magnetic dipole moment, we will put our right hand on the loop and we will move our four fingers in the direction of the current and close them. Our thumb will be the normal to the loop in this case. So by using the right hand rule, we can obtain the direction of the vector magnetic dipole moment as the sum related to our four fingers when they are turned on. So the direction of mu is that the normal vector to the plane of the coil, which is given by the right hand rule. The unit of magnetic or vector magnetic dipole moment mu is, according to this relation, n is dimensionless, I is ampere, and area is meter square. So the vector dipole moment has a dimension ampere multiplied by meter square. Now according to this, we say that the total torque in a loop would be NIA multiplied by B multiplied by sin theta, which can be simplified to be mu multiplied by B multiplied by sin theta. Or in other terms, in vector quantities, in vector product quantities, we can say that the torque equal the vector product of mu cross B. We have seen before that the cross product is the amplitude of the first vector, mu, multiplied by the amplitude of the second vector, multiplied by the sine angle between them. And its direction is normal to both mu and B. So the generalized vector relation of the torque in terms of vector magnetic dipole moment and magnetic field, applied magnetic field, the torque is a vector quantity equals mu vector magnetic dipole moment cross B magnetic field. Okay. As an example, the figure shows a rectangular 20 turns coil wire. So the number of turns here is 20. Of dimensions 10 centimeters by 5 centimeters. So the values of A and B are 10 centimeters and 5 centimeters. It carries a current 0.1 ampere. So I equal 0.1. And is hanged along one long side. It is mounted in XY plane. It is supported in XY plane. In XY plane, and the current is passing in this direction. So according to the right hand rule, it means that the normal to the loop, or the normal to the magnetic vector dipole moment of this loop, would be in the negative z direction. So this by applying our right rule hand. Put your fingers in this direction and look for your thumb. It will be in the direction of negative z. Okay. It is mounted in XY plane at angle theta equals 30 to the direction of uniform magnetic field of magnitude 0.5 Tesla. So the magnetic field has an angle 30 degrees from this XY plane. So it is required in unit vector notation what is the torque acting on the coil about the hang line. Now, if you remember the rule that we have mentioned, the torque as a vector quantity equals mu as a vector quantity cross B. So if we represented B in vector quantity and represent mu in vector quantity and we obtain the cross product between them, we can obtain the torque. Okay, let us do that. Okay, that's what we have. We have torque equals mu cross B, and N equal 20 turns coil. A and B are 10 centimeters, B 5 centimeters. The current I is 0.1 ampere, and the normal direction to the loop. By using the right hand rule, put your right hand fingers in the direction of the current I and look at your thumb. It will be in the negative Z. So the normal to the loop would be minus K, or the vector of the magnetic dipole moment would be minus K. So the magnetic dipole moment in this case, mu as a vector quantity would be NIA in direction N. So N is 20, I is 0.1 ampere, A is 10 centimeters, 0.1 multiplied by 5 centimeter, 0.05 in the direction of minus K. So it is minus 0.001 K, 0.01 K ampere meter square. Now the magnetic field B has a value of 0.5 Tesla, and it is in direction theta with respect to x, where theta equals 30 degrees. So we can analyze this vector quantity into x component and z component. So the magnetic vector quantity B would be 0.5 multiplied by cosine theta in the direction of x, I, plus sine theta multiplied by the direction k in the direction of z. And theta here is 30 degrees. So the torque as a vector quantity would be the magnetic dipole moment of the loop cross the magnetic field B. So it is minus 0.01 in direction k, cross product with 0.5 cosine theta in direction I plus sine theta in direction k. K cross I, if we apply right hand rule, K cross I, it would be in direction J. So this K cross this I would be J. K cross K, the angle between K and K is 0, so the cross product between them would be 0. So in this case, this cross multiplication would be only K cross I. And according to this, it would be minus 0.005 cosine theta in direction J. The minus is originally, and K cross I is J. And theta is 30 degrees. If we apply theta with 30 degrees, we can find out the torque in this case would be minus 0.0043 Newton meter in the direction of J. Okay.